In part B, we showed that for each n equal to 1, 2, 3, and so on, we had an independent solution un to the wave equation. Now, because the wave equation is linear and homogeneous, every linear combination of the UNs is itself a solution to the wave equation. Therefore, the most general possible solution to the wave equation is the sum of all these UNs, namely the sum from n is equal to 1 to infinity of UN. And if we replace the UN with the expression for UN we just derived in part B, we get that the general solution is given by equation 13. Now, all that remains is to determine these coefficients alpha n and beta n. And to do that, what we're going to do is we're going to impose the initial conditions 4 and 5 and invoke Fourier theory. Okay? So if you look back at initial condition 4, that told us that u of x0 is equal to f of x, where f is just some prescribed function. Okay? So what we want to do is we want to impose this initial condition in equation 13. So to do that, we need to evaluate u at time t is equal to 0. So in equation 13, if we replace t with 0, we'll get cosine of 0 and sine of 0. And recalling that cosine of 0 is 1 and sine of 0 is 0. The left-hand side here, u of x0, will work out as the sum from n is equal to 1 to infinity of alpha n, then multiplied by sine of n pi x over L. And that has to be equal to f of x. Okay? Now, if you recall from your lectures, the left-hand side here, well, that's just a Fourier cosine series. Sorry, a Fourier sine series for the function f. Which means that we can identify the alpha n's as the coefficients of the Fourier sine series. And if you recall from your lectures, alpha n in this case would be 2 over L times the integral from 0 to L of f of x bar times sine of n pi x bar divided by L dx bar. And x bar here is just a dummy variable. I've used x bar to distinguish between x. Okay, so this x bar here, it doesn't have anything to do with x, it's just a dummy variable. If you work out this integral here, you would just get some expression in n independent of x. Okay, so that's the alpha n. So for later reference, I'm just going to call that equation 14. This equation here determines the coefficients alpha n given a function f. Now, to determine the beta n's in equation 13, we're going to follow a similar procedure. What we're going to do is we're going to impose initial condition 5. Now, initial condition 5, that tells us that the derivative with respect to t of u evaluated at time 0 is equal to g, where like fg is just some prescribed function. Okay, so to impose this initial condition, what we have to do is we have to differentiate u with respect to t. So if you differentiate our series expansion 13 with respect to t, you'll get what's shown on the left-hand side here. Okay, so if we evaluate du dt at time 0, then what will we get? We'll get sine of 0 and cosine of 0. Sorry, there's meant to be a beta n here, my mistake. So we'll get sine of 0, which is 0, and cosine of 0, which is 1. So imposing the initial condition, the left-hand side would just be the sum from n is equal to 1 to infinity of n pi c times L times beta n times sine of n pi x over L. And that has to be equal to g of x. Again, we can identify the left-hand side as a Fourier sine series for the function g. Okay? Which means that the coefficients of sine, namely n pi c over L times beta n, that's the Fourier sine coefficient of the Fourier sine series for g. Okay? Which you know from your lectures that you can identify as follows. So the Fourier sine coefficient, n pi c over L times beta n, the coefficient of sine in the Fourier series, that has to be equal to 2 over L times the integral from 0 to L of g of x bar times sine of n pi x bar divided by L dx bar. And then we can just solve this equation for beta n by multiplying both sides by L over n pi c. And that would give us that beta n is equal to 2 divided by n pi c times the integral from 0 to L of g of x bar sine of n pi x bar divided by L dx bar. And we're going to refer to that as equation 15 for later use. Okay? So if you're given functions f and g, then you can evaluate these integrals to obtain explicit expressions for the Fourier coefficients. Okay? So if f and g are not given, then the solution to the initial boundary value problem we were given is complete. The solution would be given by the series 13 with the Fourier coefficients given by equation 14 and equation 15.